Here's an example that's asking you to determine all relative extrema, so relative maxes and mins, or local maxes and mins is another way of saying it. They also want the intervals where this is increasing and decreasing. And notice here that they're giving us a closed interval to work from. That's an x interval right there. And so that's going to come into play. Whenever somebody wants you to find a local max or min, relative max or min, or they want you to find where something is increasing or decreasing, that really is bells and whistles telling you that you need to run a first derivative test. First derivative test is the same process every single time you run it. That's one of the nice things about math is sometimes it's just follow the steps and you get to where you need to be. Step one of the process of following the first derivative test is, guess what? Find the first derivative. So we take the equation that they've given us and we go ahead and find the derivative of that. So finding f prime of x, this is just going to be a power rule here. We just have things being added and subtracted. So bring our power down. 5 times 3 gets us 15x. Subtract 1 from the power gets us x to the fourth. Bring that 3 down. 3 times negative 20 gets us negative 60x. And then subtracting 1 from the power gets us x squared. So step one of our process is complete. Step two of the process is now we need to find critical values. So critical values occur in two different situations. They occur when your derivative equals 0. That's the one that almost everybody picks up on. The other place, though, that they can happen is when our derivative is undefined. And so we always have to be careful for that. And so things can be undefined. Usually when you've got a fraction, if you need to look out for where you might get division by 0. If you've got a square root, remember you can't take roots of negative numbers. And then in this situation, we have endpoints of our interval. So at the endpoints of our interval, the derivative does not exist. It's undefined there. And so that's the type of undefined situation we have going on here. So we start off and we really get kind of two critical values for free. We know that x equals negative 4, one endpoint, that's a critical value, and x equals 4, that is also a critical value. Now we go back and we'll take care of the standard one, the one that everybody knows and tracks, which is setting the derivative equal to 0. So we take our derivative from step 1 and we just set it equal to 0 and we solve this for x. First thing you're going to want to look to do on a problem like this, anytime you've got a power of 2 or greater, the process is always going to probably require factoring. And that's what you're going to need to do here. So we're going to look for what we can pull out. So I can pull a 15 out of both of those pieces, and I can pull an x squared out of both. So I can pull a 15x squared out of everybody. That'll leave me with x squared up in the front, and then 15 out of 60 would be a 4. And then I pulled all of that x squared to the front, so that x squared is gone. The reason we do this now is that these things are being multiplied. We can break this up into two smaller bite-sized math problems. So whenever 15x squared equals 0, that's going to give us some critical values. And then whenever x squared minus 4 equals 0, that's also going to give us some critical values. So we'll just come through, keep doing our algebra on these little math problems here. So divide by 15, we end up with x squared equals 0. And then we'll go ahead and square root both sides of this. And we end up with x equals 0. So that's going to be a critical value for us. And then we'll keep working along with the same equation here, x squared minus 4. Go ahead and add the 4, add the 4. We end up with x squared equals 4. And then we're just going to take the square root of that. So when you square root something, remember that you're going to get the positive and the negative out of there. So we're going to get plus or minus 2, which is the square root of 4. So really we have two critical values. We've got one at x equals 2, and we have one at x equals negative 2. So in this problem, we actually have 1, 2, 3, 4, 5 critical values that we need to keep track of. So step 2 is now complete. We've got our critical values in place. And so now we're on to step 3, which is going to be where we actually do the first derivative test. And this is just a number line game. So you're going to lay out your number line, and you are going to mark your critical values. So in this situation, we had 5 critical values. We had 1 starting at our endpoint of -4. So really our number line is going to begin here at -4. That's a critical value. Then going in order, the next one would be x equals -2. The next one after that would be x equals 0. The x after that would be 2. And then from there, we've got our other endpoint, which would be x equals 4. So that's our other critical value. To do the first derivative test, we need to choose test values from each of these different intervals. So we need a value in between -4 and -2, -2 and 0, 0 and 2, 2 and 4. How many ever intervals you have, that's how many test values you need to grab. So our test value on this one, I'm going to grab -3. The test value on this one, I'm going to grab -1. The test value on this other space, I'm going to grab a +1. And then on the last one here, I'm going to go grab a +3. So these are our derivatives testing that we need to do. So it is called a first derivative test for a reason. Guess what? Because we are going to test all of these values in the first derivative. So what we need to find out now is what does f prime of -3 equal? What does f prime of -1 equal? What does f prime of 1 equal? And then what does f prime of 3 equal? So we'll come through. We're going to plug all of those into our first derivative there. And so for this one, when we plug in -3, we are going to get out a positive 675. And we don't care about the number as much as we care if it's positive or negative. So what we know right now is on that interval, our graph is positive, and so it's going up and increasing. And I always draw these arrows showing me the direction the graph is going. You'll be surprised how much that helps you understand the shape of the graph in the end. So now we'll plug in -1 to our derivative, plug in -1 into the derivative everywhere we see an x, we get -45. So in that interval there, our graph is headed down and decreasing. Plugging in 1 to the derivative, we get out again -45. So again, on this interval, we're negative and decreasing. And then plugging in 3, we end up getting out positive 675. And so on this last interval here, this thing is positive and increasing. And so at this point, you can kind of see the shape of your graph if you look at it. You've got this up into down going here, then it's down, down, and then this down into up. So before you look any further, you can kind of see to yourself, you know you at least have a max and a min going on at those 2 critical values right there. So from that first derivative test, let's go ahead and answer these questions for them. So first and foremost, they want to know what's happening as far as relative extrema. So this is relative extrema. These are going to be maxes and mins. So local maxes are relative maxes and relative mins. Like we said, just looking at the shape of this right now, maxes are always going to be an increasing section into a decreasing section. And, you know, like I said, if you draw that little shape right there, you can see for sure you've got a max happening at that critical value. So we know we've got at least one max happening at x equals -2. Mins are always going to be negative into positive. And so we already marked that. Again, if you just draw those shapes, it really helps to see. We for sure have a relative min happening at x equals 2. On this specific problem, when you have an x interval, a closed interval that you're working with here, you have to consider what's happening at those critical values at the very end of your graph. And so here it's really helpful to just kind of draw yourself out a sketch. So if I start at -4, following my arrows, the green arrow says I should go up, and then at -2, I'm going to go down. Then at 0, I kind of go horizontal for a moment, but I'm still going down. And then at 2, I come back up, and I hit my endpoint over here. So we've got that critical value, that critical value, and that critical value. Those were the ones in the middle. But at these endpoints here at x equals -4 and x equals 4, we have to consider what is the behavior there. Remember that relative maxes and mins, local maxes and mins are only saying that you are the largest or the smallest y value in your little area. So if I look at -4 here, x equals -4 on my sketch, I can see that at -4, this is the smallest point in its little neighborhood. Everything else goes up out of there. So what you're looking at here is actually another local min or relative min. So we have another relative min happening at x equals -4. Then again, looking at the other endpoint at x equals 4, this point is now the largest point in its little neighborhood. Everything else is below it. So what we're looking at over here is actually going to be another relative max. So we have x equals 4, our endpoint there is going to be a relative max. When you have closed intervals, you've got to remember to have some type of behavior, at least answer the question, what's happening at those endpoints. And then we can see that in the middle here, we ended up with that critical value was nothing. There was no max or min going on there. So we know where our relative extrema are happening, and then they want to know the intervals where this graph is increasing or decreasing. So increasing means heading up. So what we know is you just kind of read the data off of your chart. You know that between -4 and -2, this graph has got a positive derivative and headed up. At -4, it's not increasing or decreasing. It's that endpoint right there. So don't include it. So that would be from -4 to -2. And then, and again, if you kind of look at your own sketch here, you can see that that would be that point. And then it's increasing again at the very end here, where we have this other plus going on. So that would be, they like you to put a union symbol. That means connect. And then starting at our critical value of 2 and ending at 4. And don't use brackets, use parentheses. Neither one of those is included in that interval. Going on to the next one, wanting to know where these are decreasing, where it's going down, this is where they get a little tricky on you. So you go negative here into another negative there. So we're going down, and then we're going down again. A lot of people will fall for the trap here. You get almost taught it in class where they're like, oh, at this one point it's not increasing or decreasing. Well, when you go negative into negative, it is decreasing across that entire interval. Even though it goes horizontal for a second, increasing and decreasing, those are terms that mean one point is larger than the next. So when I look at this, if my point to the left here is going to be bigger than the point to the right, that still means this is decreasing. So even though I've got a critical value in the middle there, this graph is decreasing across that entire interval. So all the way through here between those two critical values. So between -2 and 2, this is decreasing. If they ask you where is the derivative negative, that's when you're going to break this up into two answers, because you would have between -2 and 0, the derivative is negative. But we do know that there is a critical value happening right there in the middle, so it does go have a 0 derivative. So that means that you don't include that as far as a negative derivative answer. So then we'd need a union symbol. And then because we need to start back up at 0 but not include 0, you would put, again, a parenthesis. And then at the end, this one ends at 2 here. So be very careful on these questions. Decreasing means that it's just continuing to go down. And that is what's happening between -2 and 2. The tangent line, the derivative value at 0, it might have a tangent line of 0, but that doesn't stop it from decreasing through that whole interval. However, it does stop it from having a negative derivative. So be super careful on the two different answers. The last move that you might want to do on a problem like this, this is kind of like a personal preference. Sometimes your teacher wants to know what is the actual max or what is the actual min. So they want you to go ahead and you need to plug these values, your relative max and min values, back into the original function. So into your starting equation. Because maxes and mins are actually the y values. The x values are just when it happens. So we would need to do a relative max, and we would say add f of -2, and we'd say at f of 4, and then we would have relative mins at f of 2 and at f of negative 4. And so you would plug those again back into your original function because that's where the maxes and mins are happening. So on f of negative 2, we would get out a positive 64. On f of 4, plugging that into the original equation, you'd end up with 1792. Plugging in 2 to the original equation, you would get negative 64. And plugging in negative 4 to the equation, you'd get negative 1792. So keep in mind that the actual maxes and mins are the y values. That's what they are. When they occur, those are the x values. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.